Here what we're going to do is take a look at some more conversions using compound units. So our initial introduction was using relatively simple units. It's just a single measurement. Compound units, we're now taking two measurements and we've combined them into a single thing. So if we look at, say, speed of your car, bike, or walk, if you were going to class, or since we're not going to class, maybe, I don't know, to the bathroom, that speed would be a distance by time. That's a compound unit, right? And really, in and of itself, that's actually a conversion factor because it allows you to convert a distance traveled to a time that it takes to make that distance. And that's kind of a neat thing. So if we were to go through and look at some examples, oh, come on, technology, thank you. We would look at, say, these kind of, and actually I'll backtrack that a little bit. We could go through and kind of solve some things out. So the first question here is, what is the speed in meters per second? So the question being asked is meters over seconds. Given information, we know the motorcycle is traveling 105 kilometers per hour. When we go through and place that in, should we be placing it 105 here or 105 on top? So on top or on bottom, which gets back to kind of the dilemma of conversions. Arguably, neither is correct. Okay? And by arguably, I mean I'm going to argue that neither of those statements is correct because the placement of that number is dependent on the units associated with it. If we go through to look at our answer, we're looking at meters, a measure of distance, over seconds, a measure of time. If we go through to look at our given information is 105 kilometers per 1 hour, which is a measure of distance over a measure of time. So it's the exact same system, just different units, which means I should be placing kilometers as a distance in the numerator, because that's where it needs to appear in my denominator, or in my answer, and then time, hours, in the denominator, because that's where it shows up in my answer, in the denominator. Now that I've got the units placed, now I can place in the numbers. 105 will go with kilometers, which is really clear to see from here, a little bit less clear to see when we're in this stupid slash notation, but note that the 105 is closer to kilometers than it is to hours when we write it out, which means the 105 belongs with our kilometers, not our hours. The number that we get placed next to hours has to be 1, because if it was anything other than 1, it wouldn't be 105 kilometers, okay, per hour. So now we would compare left to right and note that those units aren't the same and that we need to run a conversion. Both of those units are incorrect for what we're aiming for, which means both of them need to get converted. The order in which we do that does not matter because we're looking at multiplication. 2 times 3 equals 6, just like 3 times 2. So let's go ahead and take a swing at this. I'm going to go through and do kilometers first. I want to get rid of the kilometer unit. So I'm going to place it in the denominator. This would allow me to cancel it, which would be great. But, or not necessarily but, and the next part that's going to be important is that I need meters to appear in my answer. So now my question becomes, does that conversion factor exist? Is there a conversion between meters and kilometers? Well, if I've done the work that I was told to do by my chemistry instructor, I was told to memorize that kilo meant 10 to the third. The power of 10 always goes with the core unit, being meters in this case, and I do now have a conversion factor. The power of 10, as far as going into my conversion, the power of 10 is closest to the meters, so I'm going to place that power of 10, 10 to the third, next to the meters. And I'll place the 1 next to the kilometers. This works out great because now I've got meters. But before I say I'm done, I do have to acknowledge that if I ran the calculation on the left-hand side, I would have meters per hour, and I want meters per second. So now I'll launch into my next conversion. In this next conversion, I don't want hours. I want to be able to cancel that out. Okay, so what do I want to convert it to? Well, the target is to go to seconds. Okay. Does that conversion factor exist? Some people are really good at having these kind of conversions, or really probably what they're doing is running some calculations in their head, but I would argue that most people would say no, that's not an easy conversion factor to exist. So what we will do is modify it. And instead of going hours to seconds, we'll go hours to minutes. Why am I changing the seconds and not the hours? Well, I started the whole process by trying to get rid of the hours, so that's going to stay my focus. I could convert hours to days. That is a valid conversion factor, but does that get me closer to seconds? So this is where having an idea of scale comes into play. Okay, where are hours relative to days versus minutes versus seconds? And so if we looked at our conversions, days, hours, minutes, seconds, and for that matter, we could do years, decades, and so on. So if I'm at hours and I need to get to seconds, my conversion needs to pass through minutes. Going to days doesn't help me. So now I would have to go through and say, well, what's the conversion? Well, according to the conversion, 1 hour is 60 minutes. This again removes this whole concept of I need to multiply or divide by 60. The calculation, by writing the units in, it tells me that 60 shows up in the denominator. Anything in the denominator is a division. If we look at my conversions, this gets me meters per minute. I don't want meters per minute. I want meters per second, okay, which means I need yet another conversion factor. And this last conversion factor, hopefully last, minutes would need to appear in the numerator so that I could cancel my minute unit. What do I want that minute unit to become? I want it to become seconds. So again, I would ask myself, does this exist? Well, yes, it does. 1 minute equals 60 seconds. I could now go through and place my numbers, the 1 next to the minute, the 60 next to the seconds. And now if I track my units and look at what's left over, the minutes disappeared, hours disappeared, kilometers disappeared. The only thing left would now be meters per second. Now I could go through and bother to do the calculation by entering it into the calculator. There's a number down in the lower right-hand corner, and I'm not sure I believe it. But we would take our 10 to the third times 105 divided by 60 by 60. Right? And we could now punch that in and get a number. I wish I had that number. I don't. This is, again, one of those cases where Piazza could come in handy and you could check your answer against other people. But this is, again, our process. We slowly move through each of the stages and we ask ourselves, what did we want? What do we have? And we now just kind of shuffle our conversions. Most of these conversions are things that you're kind of expected to know. In the next unit, you'll be expected to know them also, but they'll be new conversions. So if you wait for the next unit to figure out how to do conversions, what you're going to end up learning is twice the amount of stuff. Both how to do the conversions, which I told you to learn now, and what are these new conversion factors. You'll have to keep track of more material at once, which will increase the odds of you making a mistake. And again, my whole goal is to minimize your mistakes. There are 2 more questions that you could go through and do here. We've got how far did the bike get and how long in hours to go 90 miles. Okay, so those are conversions that you should be able to run on your own. And again, if you've got your work, put it together, post it in Piazza, and let others go through and critique it, including me, to be able to say, yes, that's awesome, fantastic, you're on the right path. Or maybe you missed a part and this is what we need to fix. But you need that secondary critiquing to decide how you're succeeding or not. Okay, well, in this case, I do actually give you how far did the bike get in 120 seconds as we stepwise it out. Interesting stepwising it, not in the method that I've recommended, but your work should look something along these lines. Okay. Next thing we get is volumes. And volumes are a little bit weird as a complex unit or a compound unit, but we'll see why here in a second. So volumes, mathematically, if we look at a cube, are length by width by height. We're one of those dimensions. Whoa, right? Never mind. And if we look at volumes, we might go through and say, well, they're liters and milliliters. Right? Those would be acceptable volume units, and we created those probably because the length volume was confusing, because I have to go through and take length times width times height, and if I was going to measure a length, I'd be looking in meters or centimeters. The volumes that we use in the metric system, liters as a core unit, is really just a composition of the volume of a cube defined by length. 10 centimeters by 10 centimeters by 10 centimeters is defined as 1 liter. And if we go through and do the math behind that, that's 10 times 10 times 10, and that's 1,000 centimeters cubed equal to 1 liter. I kind of want to write that down. Centimeters cubed is equal to 1 liter. Right? And that might strike some bells and some familiarity in other cases, but one of the familiarities I want to point out is that if you've ever watched like a doctor show, okay, and they say, I need 15 cc's of oxytocin, that may have been a really large amount, but whatever, 15 cc's of oxytocin stat, right? And throw in a bunch of stuff. Well, what is cc? It's clearly some form of measurement that they're talking about, but what are they using? They are using cubic centimeters. Doctors are using the metric system. Okay? That's what a cc is. Okay? It's referencing the volume based off of length dimensions, which is kind of neat. Okay? So what I would like you to kind of consider here is to use some conversion skills to determine a unit factor for centimeters cubed to milliliter. So what do I mean by that? I mean, I want centimeters cubed related to milliliters. Okay? We did just cover a particular conversion factor, so we could call that as given. That's actually sort of written out there. We were given that 1,000 centimeters cubed was equal to 1 liter. Why are we placing it in that fashion? Well, that's putting the centimeters cubed, our length volument, our length measurement of volume in the numerator, and then our volume measurement of volume in the denominator. So the liters part isn't what I want, so I know I need to get rid of that. And ideally, I would bring in milliliters. This is where it would again be useful if I had memorized what milli meant. Milli was 10 to the negative 3. The power of 10 always goes with our core unit. 10 to the negative 3, 1 liter. And we can now go through and run our calculation. And if we look at that, we got a bunch of numbers, and we punched it in the calculator, we're going to get a surprisingly simple and rather silly sounding answer. 1. What does that mean? Well, that means that 1 centimeter cubed is 1 milliliter. They're actually the same thing. Okay? A single 1 centimeter cubed block is a milliliter. Even though the math looks a little bit weird, if we shuffle that math around, it helps to see our difference. 1,000 is 10 to the third. Minus 3 plus 3 is 1. Is 0. And 10 to the 0th becomes, well, 1. Okay, so it's a relatively simple calculation, but it allows us to see the relationship between those different measurements. And because it gets such a simple result, I kind of like it, because it's nice when you get simple things. Speaking of simple things, or rather not simple things, the length volume conversions can be exceptionally challenging to go through and do, because we end up falling into some of the mathematic traps that were useful to us earlier. When we talked about exponents, say 4 times 4 times 4, we could go through and simplify that calculation, right? 4 times 4 times 4, we could say was 4 cubed, okay? Where the trap comes in here is that if we rewrote that and said 4 let's do meters, 4 meters times 4 meters times 4 meters, okay? Well, what does that become? It would become 4 cubed meters cubed, okay? Also known as 4 meters cubed. Not the same as 4 meters cubed, okay? That becomes an interesting observation, okay? And for those people being like, that's such a silly statement, I would never make that mistake, you're probably one of those people that would answer the following question incorrectly, okay? So take a look at this question, okay? We want to go through and we want to determine the inches cubed, or the cubic inches from a volume that was 498 cubic centimeters. Okay, so with that, go ahead and take a swing at this one. So pause our video, click, space, whatever you want to do. And now we'll go through and attempt it. So again, what are we being asked to solve for? We want inches cubed. Given information is just 498 centimeters cubed. Centimeters cubed is a measure of volume. Inches cubed is a measure of volume. Because inches cubed is in the numerator, that means it makes sense to place centimeters cubed in the numerator as well. And we can put in our 498. Here comes the challenge. I don't want centimeters cubed, so I'll put centimeters cubed here. Ideally, I would get inches cubed placed here. And then we'll ask, does this exist? Okay. Not easily or not clearly, but I do know that 1 inch is equal to 2.54 centimeters. And so here's what happens. We've got that cubed, and people will go, oh, because of that conversion factor, I can write that. Not really, because our conversion factor was 1 inch singular equals 2.5 singular centimeters. The conversion that we're running here is not singular inches and centimeters cubed, or inches and centimeters. It's a multiple of 3, okay? Which means I could go through and say, okay, well, that's easy enough to fix. The conversion factor I've got is actually that. Fantastic. And now I'll go through and put cubed on it, okay? Which would also work, and mathematically that comes out. But mathematically and what you enter into the calculator usually end up being different things. And the end result of this is that you usually end up adding into the calculator 498 over 2.54, which is still wrong because what you haven't done is the cube inside, right? So the easiest way to ensure that you don't make this silly volume conversion mistake is to recognize that when we say centimeters cubed, that is centimeters times centimeters times centimeters. And when we look at this conversion, one of those centimeters would cancel. Only one, because there's only one there. I need to get all 3 to get rid of. So what do I need to do? I need to do the conversion again. Okay, great, that gets rid of 1 more. And it does bring in another inch. But again, I'm not there yet, so what do I have to do? I have to run the conversion yet again, 1 inch over 2.54 centimeters. This will now allow for the centimeters to cancel. And now I could enter it into the calculator. The calculation is not 498 divided by 2.54. It's 498 divided by 2.54 times 2.54 times 2.54. Okay, or 2.54 cubed, as long as you enter the cube into the calculator. If you aren't entering the cube, that's where you're getting mistakes with this. Okay, so this is the trap when it comes to length to volume conversions. This is such a big trap and such an easy kind of fix, like logically, that most faculty don't acknowledge this as a problem for students converting. How do I know this? Because I can look at the end results of where we test on this across our discipline, and we find, not surprising to me, that the vast majority of students can't get this question right. Right? And it's not because it's doing anything particularly bizarre or different, it's just that we mathematically aren't doing the work. If you write out the work, shocking, you get the answer right. Right? So that said, don't fall into the trap that nearly everybody does. Please write out your work. You get the answer right. You will take longer to get it, but you still get more points than someone that didn't get it right, but didn't get it right faster. Get the answer right. Okay? For those people that were looking for an answer on this one, this is one that I shockingly did put up the actual number, 30.3898 inches cubed. Depending on the test question, if we were looking for sig figs, that answer would show up. It would also be the incorrect answer because we were only allowed to keep 3 sig figs. So we would need to write 30.4 inches cubed to be our fully correct answer. That way we're taking into consideration significant digits when we ran our conversion. Okay. Continuing on, we can also encounter trying to get the volume of irregularly shaped objects. For instance, if we take a look at the object to the left, we've got an interesting one because that object, you might get some mathematicians being like, well, there's an oval and I can calculate the volume of an oval, and then I've got all these triangles behind it. So if we go through and do all of that, we can now determine the volume of that object, all mathematically with measurements and yada, yada, yada. That's all well and good, okay? And I fully accept that. But now what do you do for the next object, right? That crown. That becomes significantly harder to go through and get the volume of. You could still do it by approximating little cubes and triangles and things like that, okay? But that's still a challenge. If we move to the last one, which I'm not saying we should try and measure the volume of that art form, but what I'm trying to do is actually somewhat kind of graphically reference how do you measure the volume of a gas. Okay? The gas doesn't have a physical form. How would you get its volume? Okay, so if a reaction produced a gas, how do we get it? Okay? And where this is ultimately going to come back to is Archimedes was given credit for this because an object will displace a volume of liquid equivalent to its own volume. So when he got into the bath, the water rose based off of his volume. So I can take advantage of that principle to determine the volume or measure the volume for any object, regardless of its size or shape, because I just need a container that would displace that volume equally. Okay, so the example that we could look at from our textbook, we take a graduated cylinder, we mark off where the volume starts, we drop our object into it, the volume increases. It's going to increase by the exact volume of the object we put in there, which means if I want to know the volume of that green jade sample, what I have to do, thank you, would take the final volume minus the starting volume. It's an odd way to write that. And I would be able to determine that the volume of that jade object was 10.5 milliliters, relatively simply and easily, and with better precision than the assumption of all the small little measurements made of that object. Okay, and so that's why it's cool. You can do it for gases too. For instance, in this system, really what we're saying is that I'm running a reaction here, and this reaction produces a gas. If I want to know the volume of gas produced, what I can do is rig up this system. That gas builds up pressure inside this, which then pushes down on the liquid. The liquid then rises up the straw and comes out over here. So as long as I have markings over here to note the volume change, I can determine the volume of the gas. Gases can be a little bit tricky though, so I do want you to at least be aware that this experiment does have some potential flaws. Gases change their volume with temperature, and when we talk about gases in the next unit, we'll see that. Okay? And you've probably already seen it because this is why we have hot air balloons. Okay? We take an empty thing and all we do is heat up the air inside it, and what happens is the balloon expands. Okay? So volume and temperature have a very strong relationship. So I could get a volume displacement measured over here that was literally just due to the heat coming into this. Okay? So the way we would have to redesign our experiment to make sure that that wasn't an effect is that the gap between where that heat is and where my measurement is being taken, that distance needs to be a really long way off. Okay? That distance means that by the time I'm getting in here, I'm not getting a temperature effect, I'm literally getting the particles affecting this. Okay? So just something to be aware of, don't stress about it, I just thought it was neat. And then the last thing that we'll look at here, there's a link, number one, to, I think, a rather hilarious video. So go ahead and open up the PowerPoints and follow that link, because I don't think you can follow it from the YouTube video. But what we're looking at is density, which is another compound unit. There's another video that follows this that looks at the calculations of density, but here we'll just kind of address it simply. Interesting kind of observation, which is fun to play on, play on little kids. You could say which weighs more, a pound of lead or a pound of feathers. Okay? And for those of us that kind of really address that, they're both a pound, so neither one weighs more, they weigh the same thing. It turns out that this question has a lot of different kind of nuances behind it and a lot of psychologies. One of the explanations behind this has to go on the concept of density, is that relationship between mass and volume, we don't really appreciate appropriately. And so when we hear this, which one weighs more, we start factoring density into our analysis, which was really irrelevant because density isn't mass. Density is the relationship between mass and volume. So that's why the follow-up question, which one would you rather be hit? The pound of feathers is probably not that bad because the volume that mass is in is so large that if it hit you, it was going to displace and not hurt as much. Whereas a pound of lead, if that slammed into you, that's hitting in a tiny, tiny area, that's going to hurt a whole lot more. Okay? And that's kind of that argument. It's this issue with density and how our brain interprets density. Okay? Ultimately, density is the relationship between mass and volume, which really then means what we now have is another conversion factor. Okay? That conversion factor allows us to take a mass and convert it into a volume, or take a volume and convert it into a mass. Both of them would have to use density as a conversion factor to bridge that gap or that transition. Okay? So again, I'm going to plug that you go back into the lecture, click that link, because that link is kind of hilarious. And with that, I'm done. I hope you have a good rest of the day.